We left off looking at valence bonds and looking at hybridization. And when you think about hybridization, we're really talking about how do these hybridized orbitals overlap to form bonds. And the end of the presentation last time was this idea that there are two ways that orbitals can overlap to form bonds between atoms. And now we're going to get into those two forms. Now, one form is what's called a sigma bond. And a sigma bond is when you basically have a head-to-head overlapping and the electron densities are on the axes even with where the nuclei are, and so if you think of like this hydrogen-hydrogen bond, so that'd be hydrogen gas, you have two s orbitals overlapping, and they're overlapping on the same kind of axes as that the nuclei are. And then let's say for hydrogen and chlorine coming together, well, chlorine has a p orbital overlapping with an s orbital, but they overlap on the same axes that the nuclei are. So these are what are called sigma bonds. Now, the other type of bond are called pi bonds. And pi bonds are side-to-side overlapping orbitals. So rather than the orbitals being on the same axes, they're actually above and below the axes of the nucleus. So how this plays out is all sigma bonds or single bonds are sigma bonds, where basically the electrons are on the same axes as the nucleus. And this gives a stronger bond and more energy lowering when a sigma bond is formed. Now, when you have multiple bonds, so double or triple bonds, you're going to have a sigma bond, but you will also have one or two pi bonds in addition. So we'll look at maybe look at an example here. So here we have, so this is aldehyde. You've got a carbon, and it has a sp2 orbital hybridization. So it's going to have those three kind of lobes coming off. But because it is sharing two pairs of electrons between the carbon and the oxygen, the first pair of electrons is being shared within the sigma bond, okay, along the nuclei axis, but then you have the second pair that are in what is called the pi bond, and they are above and below the actual nuclear axes. So the unhybridized p orbitals overlap in the pi fashion. So you have two s's, or well, we'll look at this in class to probably clarify it a bit more. But these electrons, for you to have a double bond, those electrons can't exist within that same axis that two pairs are. So two electrons are in the nuclear axes, but there's another two electrons that are being shared, but they can't exist within the same space that the other two are. So you have these other regions. So in this case, the pi bonds for that one. Now take acetylene here, and it has a triple bond. And so with a triple bond, you are going to have a sigma bond, just like before, but you're going to have two pi bonds on different orientations to make that a triple bond. And like it says here, the two sp orbitals form a sigma bond between the carbons, and two pairs of p orbitals overlap in a pi fashion to form the two pi bonds. So when you write a Lewis structure so how do the pi bonds and the sigma bonds come into play when we're talking about resonance structure? So when we draw, so here we have, what is this? This is nitrate. So you have nitrate ion, and you've got the three Lewis structures for it. Now, if you think about it, so you could have the double bond on either one of these three oxygens. So by looking at it, you would think that one, you have two sigma bonds between the single bonds, and then you have one that has a sigma and a pi. But remember, when we were talking about if you can have multiple resonance structures, then the reality is that the bond length is not like two single bonds and one double bond. It's more like a hybrid of that. And the reason for that is because those electrons become delocalized in that p orbital space. So you get more of this lower structure in regards to how how those electrons are actually being overlapped in all of those p orbitals. So this means the pi electrons are not localized between the nitrogen and one of the oxygens, but rather are delocalized throughout the ion. So those extra electrons are kind of floating, if you will. Same thing goes for like the resonance of benzene, which we saw previously. It can have either one of those sets of, 3 pairs of double bonds, but in reality, all the bond lengths are the same, and so you're going to have a p orbital overlap that looks more like the image to the right, rather than either one of the ones on the left. So in reality, the pi electron in benzene are not localized, but are delocalized. The even distribution of the pi electrons in benzene makes the molecule unusually stable, and benzene is a fairly stable structure. And then if you plug different functional groups off of benzene, you get some really interesting compounds. And that's where we're going to stop for chapter 9. We are actually not going to get into the next pieces of the chapter. So with that, we will see you in class tomorrow.